Now, for the last topic within the general topic of logic, we're going to talk about negating statements. So given a statement R, the statement not R is called the negation of R. The process of finding not R is called negating R. So the process of finding the negation of R is called negating R. Okay, so De Morgan's laws will be very helpful here. So let's recall De Morgan's laws from a few videos ago. So the first one says not P and Q is logically equivalent to not P or not Q. And the second one says not P or Q is logically equivalent to not P and not Q. Here's an example where we use De Morgan's law. Consider this statement. We'll call it R. And the statement says you can solve it by factoring or with the quadratic formula. Doesn't matter what it's talking about. You can solve it by factoring or with the quadratic formula. And that's, we give the statement the name R. Now let us denote R as P or Q, and that will be helpful for manipulating it. So P or Q, so R says P or Q, where P means you can solve it by factoring, and Q means you can solve it using the quadratic formula. So obviously R is equal to P or Q. R says you can solve it by factoring or with the quadratic formula. So that's P or Q. Now we would like to try to find the negation of R. So the negation of this, the negation of R is this, right? So it's not P or Q. And then we use the De Morgan's law, we use the second De Morgan's law, the second one, and to see that this is logically equivalent to not P or, oops, this is a mistake. This should be and. Okay, this should be and. Okay, so now it's fixed. All right, so now let's rewrite it in English. Well, not rewrite it. Let's write the negation of R in English. So thus we have that the negation of R is you cannot solve it by factoring and you cannot solve it with the quadratic formula, right? Not P and not Q. So again, we started with a statement R and now we found the negation of R. Okay, by the way, if one is true, then the other one is going to be false. So they're not both true, but we're just seeing how we can find the negation of a statement. We're not saying that this is true. Maybe it's false, maybe it's true, whatever. But the point is just to find the negation of a statement. Another example, we use De Morgan's laws. So consider this statement. We'll call it R, and it says the numbers X and Y are both odd. So X and Y are both odd. That's what it says. That is, R says X is odd and Y is odd. Now let's say we want to find the negation of R. The negation of R is, so it would be not X is odd and Y is odd. So the negation is, so meaning now applying De Morgan's law, we get not X is odd. It is false that X is odd, or it is false that Y is odd. So what does it mean to say that X is not odd? Well, that means that X is even. What does it mean to say that Y is not odd? Well, it means that Y is even. I'm sorry, another typo, another mistake. All right, so now it's fixed. Okay, so thus we have not R, the negation of R says the number X is even or the number Y is even. All right, so R says the numbers X and Y are both odd. The negation of R says that the number X is even or the number Y is even. Okay, so interesting. So the and turned into an or, and each of the two sides flipped. Well, not flipped, meaning was negated. Okay, or another way to say this is not R, at least one of X and Y is even, right? If we say the number X is even or the number Y is even, another way of saying that is at least one of the two is even, at least one of X and Y is even. Now, how about when we want to negate a quantified statement, meaning a statement that has a quantifier or quantifiers, right? The for all or there exists. So how do we negate those kinds of statements? So here we have two rules. So the first rule says if we have something like this. So what does this say? Let's think about this. It says it is false that for all X and S P of X. In other words, it is false that P of X applies to all X and S. Okay, so that means that there has to be something in S that P of X does not apply to. In other words, this is logically equivalent to saying there exists an x in S such that not P of x. So again, this thing on the left says it is false that P of x applies to every x. In other words, there exists an x for which P of x is false, meaning that P of x does not apply for. So that's how we deal with negating a for all kind of statement. How about the other type? How about negating a there exists kind of statement? Well, let's think about this again. Well, let's think about this too, rather. So this says it is false that there exists an x such that P of x. So that means P of x does not apply to any x in S. So in other words, for every x in S, P of x does not apply. In other words, for all x in S, not P of x. Okay, so these are two very useful rules that we will use now in some examples. Here's one example. Consider this statement. The square of every real number is non-negative. This is a true statement, by the way, right? If you take any real number and you square it, right, you do it to raise it to the power of 2, the result will be non-negative. It will be 0 or positive, but non-negative. We said this is a true statement, but it doesn't really matter. We have a statement P. Okay. In logical notation, how would we express it? We would say for all x in the real numbers, x squared is greater than or equal to 0. Okay. Suppose now we want to find the negation of P. The negation of P would be not for all x in R, x squared is greater than or equal to 0. So, but now using the first rule on the top here, we can simplify this further. So this becomes there exists an x in R such that not x squared is greater than or equal to 0. And what does it mean to say that it is false that x squared is greater than or equal to 0? Well, that is saying that x squared is less than 0. So the negation of P is this, right? There exists an x in the real number such that x squared is less than 0. Now, by the way, that's false. I mean, the negation of P is false, which makes sense because P itself is true. So the negation, which is the opposite, is going to be false. So let's rewrite it in English. Thus, we have that the negation of P is the following statement. There exists a real number whose square is negative, right? Whose square is less than 0. Now, that's not true again, but it's the negation of P. The point is we want to be able to find the negation of a statement. This will be a useful skill to have in some of the proof techniques that we learn about in the next 2 weeks. Okay, another example with negating quantified statements. So consider the statement for every, we'll call it Q. For every real number x, there is a real number y for which y cubed is equal to x. In logical notation, Q can be expressed as follows. For all x in R, there exists a y in R such that y cubed is equal to x. Now, suppose we want to find the negation of Q. So the negation of Q is, well, it is false that not, in other words, not for all x in R, there exists a y in R such that y cubed is equal to x. Now, this is logically equivalent to, well, let's see. We're going to apply the not to this part. Okay, so not that. So that's going to become there exists an x in R such that, and now we have the not here, right? Not, in other words, going back to the rule, right? We apply it here and we move the not inside. So we have not, so sorry, we have there exists an x in R such that not, there exists a y in R such that y cubed is equal to x. But now we can again apply now the second rule from the previous slide. And we get this, right? So we have there exists an x in R such that for all y in R, not y cubed is equal to x, which we can rewrite as like this, right? Y cubed is not equal to x. Thus, in English, we have that the negation of x is as follows. There is a real number x, there exists a real number x, for which y cubed is not equal to x for every real number y. You know, this is a false statement, but that's not the point. The point is just showing how we take a statement in logical notation and negate it. Okay, now how about when we want to negate conditional statements? In other words, a statement of the form if P then Q. Okay. So here we have the following rule. And you can prove this rule using a truth table, but here I'll try to explain it using reasoning. So suppose we have the following thing. We have not if P then Q. So what does that mean? That means it is false that if P then Q. Now let's remember, if P then Q means that it's a promise that whenever P is true, Q has to be true. And we talked about how the only way for that promise to be false, the only way for that promise to be broken is in a case where P is true and Q is false. So in other words, if we're saying here, if we have this kind of statement that not if P then Q, meaning it is false that if P then Q, so that must be saying that P is true and yet Q is false. So this translates to P and not Q. If you're not comfortable with that explanation, you can make a truth table and show that these two statements are logically equivalent. All right, now let's use the rule in an example. So consider the statement that says, well, first of all, we'll call it the statement R, and the statement says that if X is odd, then X squared is odd. This is a true statement, by the way. We'll see how to prove it next week. So if X is odd, then X squared is odd. That's R. That's what R says. In logical notation, well, first of all, we noticed, as we talked about in the previous video, even though it doesn't explicitly say that this applies to all X, but since we have a statement of the form if something then something, we assume that it applies to all things in the relevant set. And in this case, the relevant set would be the set of integers, because if we're talking about odd things being odd, only integers can be odd. You can't have you can't have a number like 1.5 be odd. The idea of odd only applies to integers. So I'm assuming that the set that's being discussed here is the set of integers. So in other words, we interpret R as the universally quantified statement, meaning the statement with a for all at the beginning, right? For all X in Z, if X is odd, then X squared is odd. Now let's try to find the negation of this. So the negation of R would be, would be the following: not for all X in Z, if X is odd, then X squared is odd. So now we can use the rule from before to move this not inward. So this becomes there exists an X in Z such that not if X is odd, then X squared is odd. And now we can use this rule from the top here, right? Because we have a not being applied to a conditional. So this is logically equivalent to there exists an X in Z such that X is odd and X squared is not odd, not X squared is odd. Thus, we have the following. We have the negation of R is that there is an odd integer X, right? There exists an X in Z that is such that X is odd. There is an odd integer X and whose square is not odd, such that X and X squared is not odd. Okay. Now, by the way, again, this is a false statement because R is a true statement, but this was an example showing how we can negate a conditional statement.